To understand how buffer overflow can be turned into a buffer overflow attack, we need to go down a level of abstraction to look through the level of abstraction that C and C++ give us and look at the underlying machine model, the machine code, and the stack as managed by the operating system. The C stack is where local variables, like name, are stored. The stack starts at some point in memory, and as you call functions and the stack is pushed, then that makes the memory address that's used for the stack go down and down. So pushing onto the stack means making the stack pointer have a smaller number to make room for things to be put on the stack. And then popping, by returning from a function, will move that pointer back up towards the top of memory. Specifically, if we look at a main function, and instead of looking at, say, hello, we'll just abstract to some function f, a main function that calls f, and now this f is going to have a name local variable followed by a call to getS. The assembly code generated from the C code in x86-64 looks like this. The main function calls the function f, and the function f is going to make room on the stack before it calls getS. getS is supplied by the C library, so it also lives in memory somewhere. Here I'm showing hexadecimal addresses to the left of the assembly code to say where this code is sitting in memory. When we're at the call to f inside of main, that means the processor's instruction pointer is pointing at that call queue instruction. The stack pointer will be pointing to someplace in memory, representing the top of the stack, and the effect of the call queue instruction is both to change the instruction pointer to the destination. Here, this comment says f is located at this address, hex 400560. Call queue does that, but it also takes the address of the next instruction after call queue and it pushes that onto the top of the stack. That is, it decrements the stack pointer by a word or 8 bytes and writes the address of the instruction after the call into the space it just made. At this point, the function f is taking over, and the first thing it does is make more space on the stack to store local variables like name. And then I'm omitting a little bit of the code, but then we get to the call queue of getS, which is going to set the instruction pointer to jump into the getS function, meanwhile pushing again onto the stack. In this case, the address right after the call queue to getS is 400575, so that's the address that gets written. getS is going to do some work, and eventually it's going to return. That retqueue instruction is going to look at the current stack pointer, get the address that it's currently there, 400575, and use that as the new address for the instruction pointer. It will also pop the stack since it has used that return address. So call queue pushes onto the stack, retqueue takes that address that was pushed by call queue back off the stack, and that's how function calls and returns work. As f continues, it will bump the stack pointer back up, and then also return again by looking at this return address and moving the instruction pointer to that address while popping the stack.